All right, so on Part D now it says describe the rate of change of the population in New York. Now keep in mind that the rate of change here that we're talking about is a constant rate of change because we are talking about the fact that New York was linear. And so we want to state just as we had done in our linear chapter. So each year the population increases by, and now if we look back, we can see that the population, and it told us 0.07 by 0.07 million people. So again, we have an input part of our statement and an output part of our statement. Now, the same question is being asked of what the rate of change for the population of Austin, but this time we know that this rate of change is a factor because we know that the situation is exponential. And we can write this using two ways. We can talk about it in terms of the factor, and we can also talk about it in terms of its percent growth. And so we're going to start out the same way. So each year, again, having an input part of our statement and an output part of the statement, the population increases by 3.2% or by a factor of 1.032. So you can include both parts of that statement, or you can just say the population increases by a factor of 1.032, or you can just say that each year the population increases by 3.2%. So you kind of have two different ways of stating that when we're talking about an exponential rate of change. So we now want to use these functions to determine the population for each of those metro areas in the year 2100. So since we're talking about, we want to know the input, or we have an input value of 2100, and so we know that we want to find out when the input value, so we want to know what the population is in 2100, and so 2100 minus the year 2012, because that's when our data is starting, we know that our input value is going to be 88 years. And so now when we go to Desmos, we can type into our table 88, and we can see that the population actually has changed. So New York is 25 million people, but in Austin there's 29 million people. So at some point in time, those two populations will have changed in terms of which one is greater than the other one. So so we have in New York, so N of 88 is equal to, and New York's population is 25.32, and that's 25.32 million. And then A of 88, so Austin's population, 88 years from 2012, which is the year 2100, we see that it's 29.26 million. And so can we assume, so did the blogger make a correct assumption? Well, yes, provided that these populations are increasing by 0.07 million for the next 88 years, and 3.2% every for the next 88 years. So now we want to find out when those populations are the same. So we already have in each one, line 1 and line 2. So now we're going to look for when these populations intersect each other. And I can zoom out, but I'm only at year 10. So if I go to my wrench and I change my input to 100 years, so I want to go all the way up to 100 years. And I know my population outputs are somewhere around 30 million people. So I want my output to be maybe 35 million people. If I click off of it, I should be able to see this intersection point. Again, I changed my inputs to 100 years and I changed my outputs to 35 million people. And now I can see the intersection to be 82.96, 24.97. So our point of intersection, is an input of 82.96 and the output of 24.97. Okay, so what did we had line 1 and line 2 already. So at the end of year 82, or I guess at the end of year, let me rephrase that. 82 years would be 2094. The two cities or two metro areas would have the same population of 24.97 million people. Okay, this time we're going to look at a decreasing exponential. So you are working as a wastewater treatment facility. You are presently treating water contaminants with 18 micrograms of pollutants per liter. Your process is designed to remove 20% of the pollutants with each treatment. And your goal is to remove you want to make sure you have less than 3 micrograms per liter. So while we read this, we want to identify the input and the output. And so as we're thinking about what's happening, each treatment is telling you that's our input because that's happening per treatment. And then our output is going to be the pollutants that are removed. So we see that they are in micrograms. So 18 micrograms of pollutants per liter is really what our output is. So we first want to look at what is our decay factor. So again, we're thinking about a discount. So it's 100% minus 20%, which gives us 80%. So our decay factor, we can write it as one of two things. We can say it's 1 minus 0.20, or we can write the simplified version of it and 0.80. Either way. So now we want to write an exponential function. So our input is, we can say n equals number of treatments. And then our output is maybe P equals the number of pollutants per liter. So our function will be P of n. We want the initial amount, which is 18. That's our vertical intercept amount. We need the factor, and our factor is 1 minus 0.20, or we could simplify that and just do 0.80, and then we're going to raise that to the nth power. So that's one version of it, or we could write it the other way, where we have it simplified and write P of n equals 18, and now we simplify the factor and write 0.80 raised to the n power.